So this next presentation is about the project Certifiable System on Chip for Safety Critical Industrial Applications with Jan Andersson at Cobham Gaisler. So this project develops a platform with several processor cores where hardware guarantees that different software instances are isolated from each other. And the project also performs an evaluation according to common criteria of these hardware functions. So please.
Thank you. And I was introduced as being from Cobham Gaisler. That was true on Monday this week. On Tuesday, our company name changed to Front Grade Gaisler. We have partnered in this project together with ATSEC and also with Chalmers University of Technology. The background for this project is that we identified that there was a security gap in systems. So typically, or in many systems, users would rely on software functions for cybersecurity. But if you look into the documentation for example, one particular operating system that has been certified according to certain standards, you find at the end that they claim that these security features and so on, we can only vouch for them if the hardware actually behaves as documented. And in many cases, that documentation may be flawed, it's insufficient, and there could be features that have security implications that aren't listed as cybersecurity features, but that simply lack documentation. The hardware documentation is too incomplete to be able to trust that hardware does what we assume it will do. Next to that observation, there's a trend in system-on-chip designs, and that is to increase the degree of integration and the compute power on chip. So the block diagrams you see here are different generations of microprocessors from my employer. We focus on the space industry. So we have then gone from a single core implementation up to a dual core implementation, and the latest generation is you have 4 processors on chip and a lot of communication controllers on the same die. With this integration, you get more cores, you get more parallel software threads, you get sharing of on-chip resources. So while you lower the system cost for this by reducing the number of components, you pay in that you have new safety and security issues. For example, you have side channels that appear when you put these different software functions on a chip. When you had them on separate chips, they were isolated. So within our project, we wanted to address these items. So what the project does is that we extend an existing hardware design, and we intend to provide the timing isolation between software instances. So then we try to solve this integration problem. Then we also want to bridge this gap so that software can trust hardware. So we do an evaluation of the hardware platform to try to ensure that it provides these security guarantees. The overall goals formulated for the project is to increase awareness of cybersecurity and also for the hardware design. I think that's a general trend in the industry. The Spectre and other problems that have appeared in hardware platforms or that have been exploited in hardware platforms has certainly helped to raise awareness. And also the goal is again to bridge the gap between certified software and certified hardware platforms. So in the project, we perform, or ATSEC performs, a common criteria security evaluation of the hardware platform. And the intent is then that you can combine this with common criteria certified software and have a complete system that is evaluated according to common criteria. And as far as we know, that would be a first when we talk about systems of this complexity. So we do the design of the hardware platform and the evaluation work. We also do the actual implementation. So we extend a hardware prototype within this project. We also formulated a goal that we will apply this to the products, next generation products from Front Grade Gaisler, which are basically the world-leading space-grade microprocessors that are available. Europe is the leader in that area. When it comes to updating the results slide compared to my previous presentation at the last Samverkan conference, this basically exchanges the will do to have done. So we established a security target for the platform, and we have performed an initial evaluation. This also came with feedback on the documentation, and ATSEC has, for example, reviewed the specifications for our RISC-V microprocessor, and have identified areas that, like certain items that may be implementation specific, and have identified that those need to be documented for a certain actual implementation because it matters for security. So that has been very useful in improving the documentation that was existing for the platform. We developed and extended an FPGA prototype design, so we can actually try this hardware, we can run software on it. And we've also performed some outreach. We did project presentations to end users, customers, and we also participated during a HighPeak 2022 workshop in Budapest. We had some scope creep in the project. So initially, we wanted to focus only on timing isolation as a cybersecurity feature. That turned out to be very difficult, so we have also looked into functional separation. And we are actually now also adding implementation of some control flow integrity features to the platform. When it comes to strategies to increase impact of this project, we will release this as an FPGA bitstream that you can download if you have a commercial FPGA board. And we also have a long-term strategy to release building blocks as hardware open source components. When it comes to desired collaboration, if you want to play with a RISC-V platform that has these characteristics, the timing isolation features and so on, please let us know, and we will provide you with access to our prototype platform. We're very interested overall to interact with end users on requirements on security evaluations of hardware, software vendors with common criteria, certified or evaluated software products, and overall designers that may be interested in the hardware building blocks, both when it comes to a RISC-V microprocessor system or the network on chip infrastructure that comes from Chalmers. So thank you very much for listening, for your attention.